Hey Math Nines, and welcome to our discussion today. We'll be talking about topic 7.4, which is similar triangles. Last day, I introduced you to what similar objects were, and we discussed that specifically in relation to polygons. And if you might remember, similar objects have to have all their corresponding angles being equal, and all their corresponding sides should be proportional to one another, which means that if I have two objects that are similar, if I'm going to compare the scale factor of each side of those objects, of their corresponding sides, the scale factors of each corresponding side should be the same in order for those objects to be similar. Today we're going to be discussing similar objects specifically as they relate to triangles. And again, the rules haven't changed. Corresponding angles of triangles, in order for them to be similar, have to be equal, and the corresponding sides of each of the sides of the triangles have to be proportional in relation to one another. So I've got two triangles here to start off with. I've got triangle ABC, and I've got triangle, I'll just go alphabetically for now, PQR. Take a look at them, and they're also on your note package here at home if you've got that open. Take a look at them, and based on what I just gave you as a definition of what a similar triangle should look like, are these triangles similar? Pause me if you need to think about it, because here comes the answer right now. They are similar, and the reason why is if you compare them, they have three angles that are the same. You've got your B angle corresponds with your R angle, which is 62 on both of those. My A angle 75 corresponds with my Q angle of 75 there, and then I've got my C angle 43 corresponds to my P angle, which is also 43. So if I was going to write these down as two similar triangles, I have to actually put, it doesn't matter what order I put the letters in for the first triangle. But once I determine the letter arrangement for the first triangle, and I say it's similar to another triangle, I have to make sure that each of these letters corresponds to the corresponding angle that it is equal to. So for example, A matches up with 75. So that means that my corresponding angle for A is going to be Q. My B angle is 62, which means that its corresponding angle is R. And then P is corresponding to C. So I would say that ABC is similar to QRP. Now, just to put that in perspective, what if I would have called this triangle ACB? I can actually do that. But again, what I need to do is I have to make sure that my corresponding arrangements on the other triangle match the letters. So you see how I swapped around my C and my B. So here my R and my P are getting swapped around because I have to keep my corresponding angle of C, which is 43, with the corresponding P angle of 43, which would be the second letter in that case. So just keep that in mind when you're naming your triangles. One other thing about this, because all the angles are the same, then we can also make another deduction, and this is on the bottom of the slide here. Each of the sides, because we know that the angles are the same, we understand that each of the sides are going to be proportional to one another. They're going to be similar as well. So for example, side AB, which is going from my 75-degree angle to my 62 angle, that would be similar to QR, for example. And then for example, if I was going to say that my side CA would be similar to side, I have to go from 43 to 75. So CA would be similar to PQ, and so on and so forth. And you can see a few examples of those sides written down at the bottom of the slide. But so based on all that information, we can pretty much say with great certainty that those two triangles are similar to one another. Now, what I've got written here is I've got two triangles there that have been sort of drawn, and this is where if you've got your little acetate sheet, sorry, as I walked off camera to grab my prop, you may have gotten this from me in class. If you don't have one of these from me in class, you can certainly, if you've got some, you can even use, I mean, probably not the best, but you could maybe potentially use a small piece of glass if you had one kicking around, or something that's transparent to see through, is obviously going to make this very easy. So what we've got here is we've got a triangle on the top that's been basically drawn sort of like so, right? So we've got two triangles, and what we want to figure out here is we want to figure out the corresponding sides and the corresponding points of these triangles in relation to one another. So I'm going to draw my first triangle here, QRP. QP. I'm just going to draw it like that. There it is. There's my little triangle there. QPR, just like it's drawn here. And what I'm going to do now is this triangle here is essentially an enlarged version of this triangle, except it's been flipped upside down and it's been rotated like so. So it's basically that triangle now looks like that. So all I did is I took my triangle here, right? I'm going to flip it upside down to make it a mirror image of itself here, right? And then I flip it over like so. Now that I've done that, I can figure out what my corresponding sides are here. So I've got T over here. I've got R that matches up to R, and I've got the S down here. So by doing what I just did, I can now figure out what my corresponding sides are, my corresponding points are. So by doing this, I've discovered that R corresponds to R. Well, that makes sense because the R's touch one another at that point. I understand now that my Q is corresponding to my S and that my P is corresponding to my T over there. Now, these are drawn opposite of each other, and there is a mathematical proof that basically if I draw triangles like this, the angles of the corresponding sides are in fact going to be equal to one another. So basically, if I look at this angle here, and I'm going to make that angle there, I'm going to make that angle there, I'm just basically giving them little notations, that we can basically determine that all of those angles are in fact, they're all equal to one another. So the angle for, let's say, in this case, I've got it written down on the slide as TRS, which would be that angle there, or angle R. It's going to be corresponding to angle PRQ, which is that angle there, right? So each of the angles, and you can see it on the sheet here or on the notes if you've got them up in front of you there. You can see that each of those angles are in fact equal to one another because these are similar triangles. We can also now deduce that our scale factors on each of our corresponding sides, in fact, should be the same. So I'm going to grab any two sides that correspond. So I've got QP, which corresponds to ST over here. I've got a length over here of 6, and I got a length over here of 4. Well, if I take 6 divided by 4, I'm going to get 1.5 as a scale factor. This means that this triangle is being enlarged to about 150% on the other side of that flip situation. What else could I deduce? Well, if I take if I take 9 over here and divide it by 6 over here, I'm also going to get an answer of 1.5. So another 150% enlargement on that corresponding side, which would be QR, which would correspond to SR on this side. So that's also 150%. So the scale factor is equal on two sides now. They both equal 1.5. Let's take a look at the last side. The last side is 7.5 divided by 5. That's going to give me, again, 1.5 as a scale factor. All my scale factors on all my sides are the same, which means that all of those corresponding sides have the same scale factor, which means that they're all proportional to one another. Again, based on all that information, we have proportional corresponding sides. Corresponding angles are all equal to one another. Therefore, we've got that these are, in fact, similar triangles. And we're going to get back to that a little bit later in today's lesson. We're going to actually use this type of a triangle scenario to do some measurements and calculate some measurements. We'll get back to that here in a few minutes. So if I had to describe the triangle, I have to go with my corresponding sides or my corresponding angles. So I know that this is my first angle. So I'm going to start off with R. I'm going to say triangle RQP is similar to, and now I've got to get all my corresponding angles lined up here. R was the first one, so R is the same on this triangle. I went to Q, which is my dot, so my next point is going to be RS, RST. So it's going to be RQP is similar to triangle RST. Again, I can switch the order of the letters up. You can take a look on the bottom of this slide if you've got it up in front of you. I've given you 4 different scenarios, which are all correct. Again, all the letters match their corresponding angles properly. Like, for example, if I were to make this, QPR, for example, then I would have to change this to STR, again, to match my corresponding angles, that they're in the right order when I write them down as the name of the triangle. So hopefully that makes some sense there. So what can we use similar triangles for? Well, we can obviously use them to do measurements, right? I mean, obviously triangles are easy to create, and there's an example here that I'm going to give you, and it's a horribly drawn picture, but whatever. It's my version of a totem pole. But this is a great mathematical problem, and you could use this in Morinville. Like you could go, maybe you want to know how tall the St. John Baptiste Church is. You can't, well, you could climb it, but that's sort of an illegal act. But let's say you wanted to measure the height of the steeple of the church. How do you do it without actually putting a tape measure up the side of the church and trying to figure out how high it is? Well, what you do is you could basically use the shadow of the church and compare it to the shadow of a known object. When you have an object that casts a shadow, it's essentially creating a triangle, which is basically the edge of the light that's hitting the edge of the object, and that kind of creates a triangle there. So what we're going to do for this question is we've been given the height of a person. The person has got at a specific time of day. This person is 1.8 meters in height, and at a certain point of the day, that person is casting a shadow that is 1.3 meters in length. We have an unknown height for a totem pole, but we know that at the same time of day, it's casting a shadow that is 6 meters long. So the first thing we have to determine is there a relationship between these two triangles? Can we say that these two triangles are similar? If we're measuring the angle of the sun at a particular point of the day, the exact same part of the day, the angle of the sun coming down off the totem pole is going to be the same angle that's coming down off the sun on that person that's standing beside the totem pole. So technically, is that angle up here, the angle of the sunlight coming down, is it going to be the same on both those triangles? And the answer is yes, it will be. We also know that where the object meets the ground, that's going to be a right angle. So we've got two identical angles on the triangle, which automatically means that the third angle has to also be equal, because we know that the three angles of the triangle have to equal 180 degrees. So by determining that we have three angles that are the same, we can use the fact that these are now both similar triangles. Now we can use that to our advantage because we know that the scale factor on corresponding sides of triangles is going to be the same. So we can set up a ratio. We can do a cross multiply ratio to basically calculate the unknown height of the totem pole. So what do we know? Well, we know the height of the person is 1.8 meters, and we know that the shadow that that person is casting is 1.3. We know that ratio is going to be the same in the other triangle. We know that the general relationship or proportion of those two sizes is going to be the same proportion in this triangle because both the triangles are similar. So I know that my shadow being cast by the totem pole is going to be 6. So I can put 6 there underneath because it corresponds to the 1.3 meter length of the shadow being cast by the person. The person's height is going to correspond to the unknown value of the height of the totem pole. So that's where we're going to put our x value in. So I'm going to put my x value there. So I'm going to say that x over 6 is going to be equal to 1.8 over 1.3. Now I just simply cross multiply. I'm going to cross multiply. I'm going to basically multiply 1.8 times 6 divided by 1.3. And when I'm done, I'm going to get an x value of 8.3 meters. And that is in fact the height of the totem pole. So a great way to measure an object that you can't necessarily, measure from the height up. I mean, you can always measure the shadow of an object and then compare it to a shadow of a smaller object that you know the height of, and then you can just basically use triangular mathematics, in this case proportional mathematics, to basically calculate the unknown height. Okay, I'm going to give you a couple more problems here using some similar triangles. And again, if you want to pause these videos as I go, and if you want to try them out on your own, you're more than welcome to. If you see that I've kind of given you a lightning bolt moment and you can basically solve it on your own at that point, then pause me and then just try to calculate it on your own before I actually give the answer away. In this case, we're not calculating height. We're going to calculate the length or the width of a lake. So we've got a surveyor here that basically plotted out a small triangle closer to her, and then also calculated the length from her to one end of the lake. So what she's done is she's basically surveyed out a known area of this triangle Also calculating one length of the triangle here. So she's hoping that that information can allow her to basically calculate the unknown width of the lake. Well, take a look at this. Pause me if you need to. Tell me if these two triangles, do we have two triangles here that are in fact similar to one another? The answer is yes. We do have two similar triangles here. We've got a smaller triangle, which is PQJ, and it's going to be similar to the triangle HNJ. So PQJ is going to be similar to HNJ. So we know that all the angles are similar, are the same. We know that angle and that angle match. We know this angle and this angle match. We also know that that angle, well, that angle is shared by both triangles. So of course, it's going to be the same as well. Now that we know that all the angles are the same and we know that they're similar triangles, we can basically deduce that our scale factor for each side of the triangles are going to be similar. Now I've got a length here that's going to correspond to the unknown length of the lake. So let's start off with that. So I'm going to say that 320 on this triangle, and I'm just going to make sure I know how I did it on mine so that I'm doing it the same way, because there's a lot of ways you can do these. I just want to make sure that I've actually done this by the book. Hold please. I just want to make sure that I've done this correctly. Okay. Not correctly, but I'm just doing it the same way that it's showing in the notes, because I could do this more than one way and still get the same answer. So I'm going to say that 203, so we're basically saying that PQ, this is the relationship between PQ and PJ. So I've got this small triangle which has two values. I've got 230 here, and the side length here is 210. Those are the two sides that I know of this triangle, and I want to correspond them to corresponding sides here. I know that these values are going to be similar. So PQ is going to be similar to HN, and PJ is going to be similar to HJ, like so. So I have to set up, so this is my ratio for this one, that's my ratio for that one. I need the ratio for HN over HJ. HN, that's the unknown variable. I don't know that. So I'm going to put basically an HN. That's going to be an X on the top of that equation. It's an unknown. I do know the length of H to J, and there is a bit of a trick to this question. Don't use 305, because obviously the length of this triangle is 305 plus 210. So you have to add those two numbers together. That's about the only trick to this question. Other than obviously figuring out the ratio. 305 to 310 is going to give me 515. So now I've got my ratio. I know that 203 is to X as, 203 is to 210 as X is to 515, because I'm dealing with similar triangles. Again, I'm going to do some cross multiplication here. And once I'm done, I'm going to solve X. X is going to wind up being 564 meters, and that's essentially, that length is essentially my length for HN, and HN is of course the width of the lake. So the width of the lake in this question is going to give me a value of 564 meters. That's how I calculate the width of the lake. One last one, which is going to bring us back to a very similar kind of looking triangle to what we did earlier in the unit. We've got two similar triangles. We know that they're similar. We know that this is a triangle CAB, which is going to be similar to triangle CED. So again, we know the angles are going to be the same. We're looking for corresponding sides that we can make a ratio, a proportional ratio of. What we're trying to figure out here in this case is what is the width of the river. So the question is asking, a surveyor uses this scale diagram to determine the width of the river. The measurements he made and the equal angles are shown. What is the width of the river to the nearest tenth of a meter? So we want to calculate this one to a nearest tenth of a meter. So what I'm going to do now is I'm going to look at my proportional sides. Well, I know that this side is going to be proportional to this length over here, and this length here is going to be proportional to that length over there. So I'm just going to set up a little cross ratio again. I'm going to kind of remove my rapids out of the river because I'm running out of room here. I'm going to go 98.3 over 73.2 is going to be equal to in this case x, because 98.3 is proportional to x, and 73.2 is going to be proportional to 28.9. There is my cross ratio that I'm going to need to use for the equation. Now, I could have done this one of two ways. I'm not sure if I did it like that in my question. I'm just going to see basically how I set up my fractions in here. I did it a little differently, but it sort of still gives you the same idea. In this case, yeah, I kind of set it up a little differently, but this is going to work just as well. I'm going to basically say, okay, this is proportional to this, and then basically what we're going to wind up with when we're done is we're going to get a value of 38.8 meters is what we're going to get. So you can see here what I did on the board is a little different than what I did in the notes, but you can mix these numbers around a little bit in various ways and still get accurate ratios. I mean, I could have made this 73.2 over 98.3 is equal to 28.9 over x. It doesn't really matter as long as you understand which numbers are basically are kind of the corresponding sides to one another. But that's basically how you use similar triangles to basically calculate unknown distances. And that's pretty much the lesson for today. What I'll do just before we head out, I am going to get you, if you have to take a peek right up here, take a watch of this video. If you're still having some issues with similar triangles, this video will give you a quick little, another look, I guess, at similar triangles if you need maybe a second opinion on how they actually work. For homework tonight, you're going to complete the following questions. You're going to complete questions 4, 5C, 6, 7, 9, 10, 11, 12, and 15 on pages 349 to pages 351 in your Math Makes Sense 9 textbook. And coming up tomorrow or very soon, you're going to get yourself a quiz coming up covering topic 7.1 to 7.4, which is the first half of this unit. If you need some extra practice on that, it's not for homework, but you can certainly do some practice when you're preparing for that quiz. You can look at questions 1 to 7 on page 352 for some extra practice if you feel like you need some to get ready for that quiz. It'll be coming up very, very shortly. That's it for today. Next time, won't you join me for topic 7.5, getting into the second half of the 7th unit. We're going to be looking at reflections and line symmetry coming up next time. Thanks for tuning in, and as always, we will see you very soon.